April 28, 1869, the Nevada Desert. Charles Crocker stood before 1,400 railroad workers as the sun rose over what would become the most impossible day in American construction history. European-trained engineers had calculated the absolute limits of track laying: steel rails weighing 560 pounds each, sequential construction methods perfected over decades, maximum daily progress, 7.5 miles achieved by the Union Pacific's best crews using Irish and German workers. The mathematics were simple, they said. Physics doesn't negotiate with ambition. But 8,000 miles from European engineering schools, something was about to shatter every assumption about what American workers could achieve. Chinese immigrants, dismissed as too small for railroad construction, had spent months developing methods that defied everything the establishment knew about moving steel and earth. No European manual described their techniques. No engineering textbook explained their system. Yet, as the first supply train reached the end of track that morning, these workers began demonstrating why American innovation had never depended on following someone else's rules. Charles Crocker pulled his coat tighter against the February wind as he surveyed the 31 miles of Central Pacific track, stretching east from Sacramento into the Sierra Nevada foothills. Each mile had cost more than the railroad could afford, and 1,500 miles of impossible terrain still lay ahead. The Union Pacific was averaging 2 miles of track daily across Nebraska's forgiving plains, while Crocker's crews struggled to complete 2 miles per month through California's granite mountains. Every morning brought fresh resignations from Irish workers who'd rather try their luck in San Francisco saloons than face another day of blasting through solid rock. The numbers told a story of impending disaster. Monthly turnover had reached 80% among white workers. Wages climbed higher each week as Crocker competed with California's gold fields and lumber camps for men willing to handle dynamite and sledgehammers. The Central Pacific was hemorrhaging cash at a rate that would bankrupt the company within 6 months unless something changed dramatically. In his Sacramento office, surrounded by engineering reports and cost projections that grew more alarming each day, Crocker faced a crisis that threatened to kill America's transcontinental railroad dream before it reached Nevada. The engineering establishment had already delivered their verdict on his workforce problems. Professor Theodore Judah's detailed surveys concluded that railroad construction through the Sierra Nevada required workers weighing at least 160 pounds to handle 560-pound steel rails effectively. European-trained engineers had calculated the optimal strength-to-weight ratios for moving heavy materials across difficult terrain. Their mathematics were precise and unforgiving. Chinese immigrants, they noted with scientific certainty, averaged 110 pounds and stood barely 5 feet tall. The conclusion was obvious to anyone who understood basic physics. Celestials, as newspaper editorials called them, were fundamentally unsuitable for American railroad construction. Moving steel rails up mountain grades required brute strength that small men simply could not provide. The engineering journals were unanimous in their assessment, but Crocker had noticed something the experts missed during his frequent rides through the California mountains. Chinese immigrants had built the state's most challenging mountain roads, carving impossible ledges through granite cliffs where other crews had failed. They'd moved tons of rock by hand, creating pathways that defied conventional engineering wisdom. More importantly, they never missed a day's work, never complained about conditions, and never demanded higher wages when faced with difficult tasks. Construction foreman James Harvey Strobridge exploded when Crocker suggested hiring 50 Chinese workers as wagon fillers for the lowest railroad jobs. "I will not boss Chinese," Strobridge declared, his weathered face reddening with anger. "I don't think they could build a railroad. Give me white men, and I'll show you what real construction looks like." Strobridge had spent 2 decades managing construction crews from New York to California, and his experience told him that railroad work demanded the kind of physical strength that only Irish and German immigrants possessed. Despite Strobridge's objections, Crocker authorized the experimental hiring of 50 Chinese workers who reported to the construction camp at Auburn in March 1865. Within 1 week, they had completed more roadbed preparation than the previous Irish crew had managed in an entire month. The Chinese workers arrived before sunrise, worked through conditions that sent white workers to their tents, and maintained a pace that impressed even the skeptical Strobridge. Quietly, without fanfare or official announcements, Strobridge hired 50 more Chinese workers, then 500 more. Word spread through San Francisco's Chinatowns and across the Pacific to Guangdong Province that the Central Pacific offered steady work at fair wages. By 1867, 12,000 Chinese workers comprised 80% of the Central Pacific workforce. Yet Eastern newspapers continued printing editorials about the folly of relying on Oriental labor for American construction. The transformation was remarkable but largely invisible to the engineering establishment. Chinese workers had developed construction techniques that European manuals never described. Instead of relying purely on individual strength, they created coordinated systems that multiplied efficiency. While Irish crews worked as individuals competing for the foreman's attention, Chinese workers functioned as integrated teams where every man understood his role in achieving collective goals. They brought specialized skills that white workers lacked. Many had experience with explosives from Chinese mining operations, knowledge that proved invaluable when blasting through Sierra Nevada granite. Their precision with hand tools exceeded anything Strobridge had witnessed in decades of construction work. Most importantly, they approached engineering problems with innovative solutions rather than defaulting to established methods that often proved inadequate for mountain construction. As the Central Pacific pushed through Nevada's desert toward Utah in early 1869, they faced their most formidable challenge yet, the Union Pacific's track-laying machine. Led by the Casement brothers, Union Pacific crews had systematically broken world records for railroad construction speed. Their most recent achievement, 7.5 miles of track laid in a single day, had been declared by railroad executives from New York to London as the absolute limit of human engineering capability. The engineering logic seemed unassailable. Track laying required sequential operations that could not be rushed without compromising safety and quality. Rails had to be unloaded, positioned, spiked, and aligned in careful order. Each step took a specific amount of time based on the weight of materials and the physical capabilities of workers. European engineering studies had calculated these limitations with mathematical precision. At a heated meeting with Union Pacific Vice President Thomas Durant, Charles Crocker made the bet that would change everything. He wagered $10,000, equivalent to over $200,000 in modern currency, that his Chinese workers could lay 10 miles of track in a single day. Durant laughed openly at the proposal. "Impossible," he declared with the confidence of a man who understood railroad engineering. "The physics simply won't allow it." European engineering journals had published detailed studies proving that rail laying was fundamentally limited by the sequential nature of track construction and the weight ratios of materials to men. On April 27, 1869, Crocker's crews managed only 2 miles of track, a humiliating failure that seemed to confirm every expert's prediction about the limitations of Chinese labor and the impossibility of breaking established engineering barriers. Before sunrise on April 28th, Charles Crocker and James Strobridge faced 1,400 volunteers gathered in the pre-dawn darkness, nearly every able-bodied worker on the Central Pacific payroll. The humiliating failure of the previous day had transformed into something unprecedented, a unified determination to prove that American railroad construction could transcend every limitation the engineering establishment had declared absolute. These weren't just Chinese workers anymore, but integrated teams combining the precision and coordination the Chinese crews had perfected with the raw strength of 8 Irish rail handlers who could muscle 560-pound steel rails into position. What emerged from that pre-dawn gathering would revolutionize American industrial construction forever. Crocker had spent the sleepless nights studying the Union Pacific's methods with engineering precision, identifying the fatal flaw in traditional track laying that had limited railroad construction for decades: sequential bottlenecks. One crew would unload rails from supply cars, then wait while the next crew positioned them on roadbed ties, then wait again for spikers to drive home the connecting bolts, then wait once more for alignment crews to verify gauge and grade. Each step depended on the completion of the previous step, creating inevitable delays that no amount of individual worker strength could overcome. The Chinese workers had developed something that defied every principle in European engineering manuals: parallel processing applied to railroad construction. Instead of sequential operations, they had created simultaneous workflows where multiple specialized teams operated independently while maintaining perfect coordination. 5 supply trains waited on specially constructed sidings, each loaded with exactly 16 flat cars carrying precisely 2 miles worth of materials, rails, spikes, bolts, and tie plates calculated to the pound. But the revolutionary innovation wasn't in the supply system. It was in the deployment of specialized teams positioned every 240 feet along the surveyed route. As the first supply train reached the end of track at sunrise, teams of 6 Chinese workers with modified handcars were already in motion. They had transformed the standard unloading process into something that resembled factory production more than traditional construction work. Rails flew off flat cars in 80 seconds per car, as coordinated crews used leverage and timing instead of brute strength. Within minutes, the rhythm accelerated to 75 seconds per car. Then 60 seconds as the teams found their perfect synchronization. Behind the supply teams came the rail handlers, 8 Irish workers who had adapted their individual strength to the Chinese coordination system. Instead of competing with each other for the heaviest lifts, they functioned as precision instruments, placing 560-pound rails into exact position with movements that appeared choreographed. Each rail landed perfectly aligned with the previous one, eliminating the time-consuming adjustments that had slowed traditional crews. The breakthrough came in the supporting operations that traditional railroad construction had never systematically organized. While European methods treated track alignment, spike driving, and gauge verification as separate sequential steps, the Chinese had created integrated teams where straighteners began aligning rails before the Irish handlers had finished positioning them. Gaugers verified the 4-foot 8.5-inch spacing using precision tools they had crafted themselves, while spikers drove exactly 4 spikes per rail joint with sledgehammer blows timed to a rhythmic count that eliminated wasted motion. Each Chinese worker had been assigned one specific task and had practiced that task to absolute perfection. No worker attempted to do everything. Every worker excelled at one thing. The result was continuous flow that eliminated the start and stop rhythm that had characterized railroad construction since the first tracks were laid in England decades earlier. Traditional crews worked in waves, periods of intense activity followed by waiting periods while the next phase began. The Chinese had created constant motion where every minute produced measurable progress. The supply system supporting this revolutionary approach was equally innovative. Instead of the standard method where empty cars had to retreat before loaded cars could advance, Chinese gangs had developed a leapfrog system using temporary side tracks. Loaded trains pushed forward on parallel routes while empty trains pulled back on the main line, creating continuous material flow that never interrupted the laying crews. No waiting periods, no supply bottlenecks, no coordination delays between different crew functions. Union Pacific representatives who had arrived expecting to witness another Chinese failure found themselves taking detailed notes on construction methods that had never been described in any engineering textbook. Army officers dispatched from Washington to observe the work reported back to federal authorities that Chinese workers had achieved mechanical precision previously seen only in factory production, not outdoor construction projects. By 10 in the morning, the crews had laid 3 miles of track with quality that exceeded standard specifications. Rails were aligned within tolerances that surpassed what most established crews achieved when working without time pressure. Spike placement was mathematically precise. Gauge measurements were perfect across every rail joint. The continuous workflow had not compromised construction quality. It had enhanced it by eliminating the Russian wait cycles that caused most construction errors. At noon, they had completed 6 miles of track that met every engineering standard the Central Pacific had established for permanent railroad operations. Union Pacific observers who had initially dismissed the attempt as impossible now found themselves calculating whether their own world record 7.5-mile day might be vulnerable to Chinese innovation. The mathematical precision they were witnessing contradicted fundamental assumptions about the relationship between speed and quality in heavy construction work. The Chinese workers showed no signs of fatigue despite maintaining a pace that would have exhausted traditional crews within hours. Their systematic approach distributed physical effort across specialized teams while eliminating the energy waste that came from coordination delays and repeated positioning adjustments. Every motion served a specific purpose. Every team function integrated seamlessly with supporting operations. The result was sustainable productivity that could maintain maximum output across extended time periods. Telegraph operators began transmitting hourly progress reports to Sacramento, San Francisco, and eventually New York as word spread that something unprecedented was occurring in the Nevada desert. In railroad offices across the continent, executives who had dismissed Chinese labor capabilities found themselves confronting evidence that challenged everything they understood about construction engineering and workforce management. The afternoon sun blazed across the Nevada desert as the Chinese crews entered what observers would later describe as a state of mechanical perfection that defied every principle of 19th century construction management. What had begun as an impossible challenge had transformed into something that resembled precision manufacturing more than traditional railroad work. The continuous workflow that had carried them through the morning hours was now operating at a level of coordination that stunned even the most experienced construction foreman watching from the sidelines. Traditional railroad construction had always been defined by its stop-and-start nature. Crews would unload materials, then pause while positioning teams arranged rails, then wait again while spikers drove connections, then halt once more while alignment specialists verified specifications. The Chinese workers had eliminated every pause, creating a flowing rhythm where each specialized team began its function before the previous team had completed theirs. Rails moved from supply cars to roadbed in one continuous motion, with positioning, spiking, and alignment occurring simultaneously rather than sequentially. James Strobridge rode alongside the advancing crews, timing their operations with a precision that reflected his growing amazement at what he was witnessing. Rail cars were being cleared in 60 seconds each, faster than he had thought physically possible given the weight of the materials involved. But the Chinese had developed leverage techniques that multiplied individual strength through coordinated group effort. Six-man teams could move 560-pound rails with the same efficiency that traditional eight-man crews achieved when working without time pressure. The straightening teams were operating with mathematical precision that exceeded what most established crews achieved during careful, unhurried work. Using handmade tools crafted specifically for rapid gauge adjustment, Chinese workers were aligning rails to the required 4-foot 8.5-inch specification within tolerances measured in fractions of inches. Every rail joint was positioned perfectly before the spikers reached it, eliminating the adjustment delays that typically consumed hours of construction time. Behind the rail layers came the spiking crews, driving exactly 4 spikes per rail joint with sledgehammer blows, timed to a rhythmic count that had evolved throughout the morning. The sound created by dozens of synchronized hammers produced a steady percussion that could be heard miles away, a mechanical rhythm that announced to the desert that something unprecedented was occurring. Each spike was driven home in precisely the number of blows required, with no wasted motion and no missed strikes that would require repositioning. The supply system supporting this remarkable pace had evolved into something that resembled a military logistics operation more than traditional construction support. Chinese gangs had refined their leapfrog method to the point where loaded supply trains were advancing on temporary tracks while empty trains retreated on the main line, creating material flow that never interrupted the laying crews. Flat cars loaded with exactly the right quantities of rails, spikes, and connecting hardware arrived at the end of track precisely when needed, with no excess inventory and no supply shortages. Union Pacific representatives who had traveled from Omaha to witness what they expected would be a spectacular Chinese failure found themselves frantically taking notes on construction methods that contradicted everything they understood about railroad engineering. The sequential limitations that had defined track laying since the first railroads were built in England appeared to have been overcome through coordination techniques that no engineering school had ever taught. Speed and quality, traditionally viewed as competing priorities, were being achieved simultaneously through systematic approaches that eliminated waste motion and coordination delays. Army officers dispatched by the federal government to observe the work sent telegraph reports to Washington, describing construction techniques that resembled factory assembly lines applied to outdoor heavy construction. The military implications were obvious to officers trained in logistics and engineering. If Chinese workers could achieve this level of coordination and productivity in railroad construction, similar principles might revolutionize military engineering, bridge construction, and large-scale infrastructure projects across the American continent. Telegraph operators in temporary stations established along the route began transmitting progress reports every hour to railroad offices in Sacramento, San Francisco, and New York. By 2 in the afternoon, they had completed 7 miles of track that met every specification the Central Pacific had established for permanent railroad operations. By 4 in the afternoon, 8 miles were finished, with quality standards that exceeded what most crews achieved when working without any time pressure whatever. The Chinese workers showed no signs of the fatigue that would have crippled traditional crews maintaining such a pace for extended hours. Their systematic distribution of physical effort across specialized teams had created sustainable productivity that could maintain maximum output indefinitely. Every worker understood exactly what his function required and performed that function with precision that eliminated energy waste. No worker attempted tasks outside his specialty. Every worker excelled within his assigned role. Charles Crocker rode back and forth along the completed track, testing rail alignment and spike placement with the thoroughness of an engineer conducting final inspection. Every rail was positioned to specification. Every gauge measurement was precise. Every spike was driven flush with the rail base. The continuous workflow had not compromised construction quality in any measurable way. Instead, it had enhanced quality by eliminating the rushed corrections that typically followed coordination delays in traditional construction. As the afternoon shadows began lengthening across the desert, observers realized they were witnessing something that would change American industrial construction forever. The Chinese workers had proven that European engineering limitations were not laws of physics, but assumptions based on construction methods that had never been systematically analyzed and improved. Speed and quality could coexist when workflow was designed around coordination rather than individual strength. Precision could be maintained at maximum pace when every worker specialized in one perfectly practiced function. By 5 in the afternoon, 9 miles of track stretched behind the advancing crews, each mile meeting specifications that would support locomotive traffic at speeds exceeding 40 miles per hour. The mathematical impossibility that Union Pacific executives had declared with such confidence was being systematically disproven by immigrant workers who had approached engineering problems with innovation rather than accepting established limitations as permanent constraints on human achievement. At 12 minutes past noon, the perfect machine ground to a devastating halt. The surveyed route curved uphill through a rocky outcrop at mile 7 that required every rail to be bent by hand using blocks and sledgehammers, a process that transformed their revolutionary continuous workflow back into the sequential bottlenecks that had limited railroad construction for decades. Worse, Chinese workers discovered that the ground preparation crews had failed to properly grade the roadbed beneath the rocky section. They were attempting to lay track over uneven ballast that could never support locomotive traffic, much less the high-speed operations the Central Pacific demanded for transcontinental service. For 30 agonizing minutes, 1,400 workers stood idle while the systematic coordination that had carried them through 9 miles of desert track faced its first insurmountable obstacle. Union Pacific representatives, who had spent the morning frantically taking notes on Chinese construction methods, now exchanged knowing glances and relaxed visibly. European engineering principles were reasserting themselves exactly as Thomas Durant had predicted. Physics always defeated optimism. Mathematical limitations could not be overcome through immigrant determination alone. James Strobridge surveyed the chaos with growing alarm as specialized teams that had functioned as precision instruments suddenly found themselves with nothing to do. Rail handlers stood beside perfectly positioned supply cars while straighteners and spikers waited for rails that could not be installed until the grade problems were resolved and the track bending operations were completed. The continuous material flow that had sustained their record pace was backing up like water behind a dam, creating exactly the kind of coordination breakdown that traditional railroad construction had always accepted as inevitable. Durant's representatives began calculating how long the delay would extend the overall completion time, clearly satisfied that their $10,000 wager was safe. Hand-bending rails was notoriously slow work that required careful heating and gradual adjustment to prevent metal fatigue. Regrading roadbed ballast meant removing and repositioning tons of carefully placed stone and earth. Combined, these operations would consume the rest of the daylight hours and probably extend into the following morning, making the 10-mile goal mathematically impossible, regardless of how efficiently the crews had operated during the morning hours. Charles Crocker dismounted from his horse and walked among the idle workers, seeing in their faces the same resignation that had characterized every major construction setback he had witnessed during 4 years of Sierra Nevada railroad building. The Chinese workers were conferring quietly in Cantonese, while the Irish rail handlers sat down in whatever shade they could find, clearly expecting an extended break, while supervisors figured out how to proceed with operations that had no systematic solution. But this was precisely the moment that demonstrated why Chinese workers had become indispensable to American railroad construction despite every prediction from the engineering establishment. While European-trained supervisors would have called for specialized equipment and additional personnel to address problems outside normal construction parameters, the Chinese crews did not pause to assign blame or argue about whose responsibility the complications represented. Instead, they deployed the same collective problem-solving approach that had carried them through granite tunnels in the Sierra Nevada, where individual strength was meaningless and survival depended on coordinated innovation. Strobridge watched in fascination as the Chinese workers implemented a solution that appeared nowhere in any construction manual he had studied during 2 decades of railroad work. Without waiting for supervisory direction, half the crews began regrading the problematic roadbed section using improvised tools created from available materials. They had identified wooden planks, iron bars, and rope sections that could be combined into effective grading equipment, transforming what should have been a specialized engineering operation into a coordinated manual process that required no equipment delays. Simultaneously, the remaining Chinese crews established a rail bending operation that converted what had always been a one rail at a time process into something resembling assembly line production. Traditional rail bending required heating each rail individually over coal fires, then carefully adjusting the curve using heavy hammers and positioning blocks. The Chinese workers had created multiple bending stations where several rails could be processed simultaneously, with specialized teams handling the heating, positioning, hammering, and quality verification as parallel operations rather than sequential steps. The improvised rail bending system operated on the same principles that had revolutionized their track laying operations. Instead of one crew doing everything to one rail before moving to the next rail, multiple specialized teams worked on different aspects of the bending process across several rails simultaneously. Heating teams maintained optimal temperatures while positioning teams aligned rails in custom-built fixtures. Hammering teams shaped the curves while verification teams checked each rail against precise templates they had created from surveying measurements. Within 20 minutes, the regrading operation had restored proper ballast alignment across the entire problematic section. The rocky outcrop that had seemed like an insurmountable obstacle was transformed into a solid foundation that could support locomotive traffic at maximum authorized speeds. Chinese workers had accomplished in 20 minutes what traditional crews would have required hours to complete, using nothing but manual labor and tools improvised from construction materials already available on site. The rail bending operation was producing curved rails at a rate that exceeded what specialized rail shops achieved using permanent equipment and experienced metalworkers. Each rail was bent to exact specifications that matched the surveying requirements, with curve tolerances that met Central Pacific standards for high-speed operations. Quality verification confirmed that every rail would integrate seamlessly, with the straight sections already installed, maintaining the precise 4-foot 8.5-inch gauge the Transcontinental Railroad Service demanded. By 1 o'clock in the afternoon, the Chinese crews were not merely back on schedule, they were ahead of their morning pace. Having completed 7 miles of track that included the most challenging engineering obstacles they had encountered, during the entire 10-mile attempt. The 30-minute delay had been transformed into a demonstration of problem-solving capabilities that no engineering school had ever taught and no construction manual had ever described. Union Pacific observers who had relaxed during the initial crisis now found themselves confronting evidence that Chinese workers possessed adaptation capabilities that transcended individual technical skills. The ability to innovate systematic solutions to unexpected problems using only available materials and coordinated group effort represented a form of engineering intelligence that challenged fundamental assumptions about the relationship between formal training and practical capability. Telegraph operators resumed their hourly progress reports with updates that reflected growing amazement at what was occurring in the Nevada desert. Railroad executives across the continent who had dismissed the 10-mile attempt as impossible were now calculating whether their own construction capabilities might be fundamentally limited by methods they had never questioned. The final 6 hours transformed from railroad construction into something approaching industrial theater as telegraph lines carried hourly updates across the American continent. In Sacramento, crowds gathered around newspaper bulletin boards where reporters posted progress reports as they arrived from the Nevada desert. In New York, Wall Street traders placed bets on whether Chinese workers could achieve what European engineering had declared mathematically impossible. In London, railroad executives requested detailed technical reports on American Oriental construction methods that were challenging fundamental assumptions about heavy construction capabilities. What the Chinese workers had achieved during the afternoon crisis had elevated their systematic approach into something that resembled precision manufacturing applied to outdoor construction. The rail-bending innovation and improvised grading operations had demonstrated problem-solving capabilities that transcended individual technical skills. Now, with clear desert stretching ahead for the final 3 miles, they were operating at a level of coordination that stunned even the most experienced observers who had witnessed railroad construction across multiple continents. At 3 o'clock, 8 miles of track lay behind the advancing crews, each mile meeting specifications that would support locomotive traffic at speeds exceeding 40 miles per hour. The Chinese supply teams had refined their logistics system to the point where materials appeared at the end of track faster than the laying crews could install them. Flat cars were being cleared in 55 seconds each, with rails moving from supply trains to roadbed positions in one continuous motion that eliminated every pause that had characterized traditional construction methods. The Irish rail handlers, energized by the precision of their Chinese teammates, were moving 560-pound rails with efficiency that exceeded anything James Strobridge had witnessed during 2 decades of managing construction crews. The integration between Irish strength and Chinese coordination had created something that neither group could have achieved independently. Each rail landed in perfect position for the straightening teams, who verified 4-foot 8.5-inch gauge specifications within tolerances measured in fractions of inches. At 5 o'clock, 9 miles were completed, and every worker understood they were making history. The mathematical impossibility that Union Pacific executives had declared with scientific certainty was being systematically disproven by immigrant workers who had approached engineering limitations as problems to be solved rather than boundaries to be accepted. Telegraph operators transmitted updates to railroad offices across the continent. 9 miles completed, quality exceeds standard specifications, 1 mile remaining. The final mile stretched across perfectly flat desert that provided ideal conditions for maximum construction speed. Chinese supply crews had refined their coordination to mechanical precision, with loaded trains advancing on temporary tracks while empty trains retreated on the main line. Material flow had achieved perfect synchronization with laying operations, eliminating every supply bottleneck that had limited traditional railroad construction since the first tracks were laid in England decades earlier. Charles Crocker rode alongside the advancing crews, calculating that they would complete 10 miles with daylight to spare if their current pace continued. But more importantly, he was witnessing quality standards that exceeded what most established crews achieved when working without any time pressure. Every rail was aligned to specification. Every spike was driven flush with rail-base connections. Every gauge measurement met Central Pacific requirements for transcontinental railroad operations. As the sun approached the western mountains, casting long shadows across the Nevada desert, the final supply train advanced to the end-of-track position. Chinese workers had positioned the last rails, spikes, and connecting hardware with mathematical precision, ensuring that materials would be available exactly when and where the laying crews needed them. No excess inventory, no material shortages, no coordination delays between different crew functions. The spiking crews were maintaining their rhythmic percussion that had characterized the entire day's operations, driving exactly 4 spikes per rail joint with sledgehammer blows, timed to eliminate wasted motion. The sound of synchronized hammers created mechanical rhythm that announced across miles of desert that something unprecedented was occurring. Each spike was driven home in the minimum number of blows required, with precision that reflected perfect coordination between individual workers and collective objectives. Union Pacific representatives who had arrived expecting to witness Chinese failure were now taking detailed notes on construction methods that contradicted everything they understood about railroad engineering. Speed and quality, traditionally viewed as competing priorities in heavy construction, were being achieved simultaneously through systematic approaches that eliminated waste motion and coordination delays. The sequential limitations that had defined track laying for decades appeared to have been overcome through innovation that no engineering school had ever taught. At 7 o'clock in the evening, as the final spike rang home, Charles Crocker climbed onto a supply car and shouted one word that echoed across the desert: "Done." Telegraph operators immediately transmitted the news to Sacramento, San Francisco, and New York. 10 miles, 56 feet of track completed, 12 hours total construction time, world record achieved. But the ultimate proof came minutes later when a Central Pacific locomotive, pushed by 2 engines for maximum power, roared over the newly laid track at 40 miles per hour, faster than most trains of the era traveled on established lines with decades of settling and maintenance. The track held perfectly under the tremendous stress. Every rail remained in precise alignment. Every spike connection maintained structural integrity. Every gauge measurement stayed within required tolerances. Chinese workers had not merely set a world record for construction speed, they had built track that exceeded engineering standards for quality and structural reliability. The mathematical impossibility that European engineering had declared with scientific certainty had been overcome through systematic innovation that challenged fundamental assumptions about the relationship between speed, quality, and human capability in heavy construction operations. Union Pacific Vice President Thomas Durant approached Charles Crocker with a check for $10,000, equivalent to over $200,000 in contemporary currency, acknowledging that Chinese workers had achieved what he had declared physically impossible. But Crocker's real victory arrived the following morning in telegrams from European railroad companies requesting detailed technical information about American-Chinese construction methods that were revolutionizing industrial construction across the continent. The world record set by Chinese workers on April 28, 1869, remained unbroken 155 years later, but more importantly, it had proven that American innovation thrived when immigrant determination was combined with systematic engineering approaches that challenged conventional limitations rather than accepting them as permanent constraints on human achievement.